All right, so this recording is my presentation for the final project, the atomic spectroscopy project. Let's go ahead and get started. So, oops, there we go. So the goal of this project, of course, was to identify unknown elements in 8 different discharge tubes we were given. So a little bit of background. These spectral lines were discovered in 1814, but it would be about 100 years before people really knew what they were. And quantum mechanics actually was successful in explaining what these spectral lines were, where they came from. So what's actually going on here, as we all know, is you have an electron transition occurring between orbits. And when you have an electron in a higher energy orbit that drops down to a lower state, perhaps to the ground state, a photon is emitted. Based on the change in energy, that will determine the wavelength, and that'll determine where you see that spectral line, at which part of the EM spectrum that falls in. So our procedure here, we were given experimental data. This was taken with a digital spectrometer, and we had, for reference, the database from the National Institute of Standards and Technology. And so what we would end up doing with each element was, well, we would know where the spectral lines occur, and we would match that with, we would match the experimental spectra with the database, which contains all the possible transitions that are known for any given element. So one other thing I did too, I found this helpful. I took pictures actually of the spectra of each lamp. This was using the visual spectrometer, and this was really just more qualitative. Helped me visualize exactly what was going on, exactly what I was looking at. But again, the actual analysis was done using the digital data. So we start out, we have hydrogen and helium to identify, of course, the 2 most common elements in the universe. So as we know, hydrogen actually has a pretty simple spectrum, and you can predict it using the equation that we'll get to in a moment. The Balmer series describes the transitions that occur that show the visual part of the spectrum, the strongest lines for hydrogen. And the strongest line is 656 nanometers. It's a deep red. It's called hydrogen alpha as well, often, and a weaker line at about 486. And this was pretty straightforward to match with the database. This is lamp 2. Now, something we had to do as well was calculate, using our experimental data, the Rydberg constant for hydrogen. Now, we are going to be looking at this n equals 3 to n equals 2 transition, which of course is that 656.4 nanometer photon is emitted. So we have here the Rydberg equation, which of course we can solve for the Rydberg constant, and we find the Rydberg constant that we calculated with the experimental data is, to the significant figures that we have, it's identical with the one found in our textbook. So that's good. And next, we need to identify helium, which is another simple spectrum, a little bit more complicated, and it has some strong lines. For example, at 447, 587, 667 nanometers. And there are other strong lines outside the visible range, but these are really the characteristic lines, and a couple others as well for helium. And we match this with lamp 4. Right, and so another thing we had to do here was identify which electron transitions correspond to the wavelength of photon that's emitted. And something to mention here, actually our error that we determined for the wavelength, we took the half width, half maximum of many different peaks, averaged them together. We found an error of about 1 nanometer is what we can expect for the discrepancy between the database and our experimental data. So for approximately our experimental wavelengths, we find, for example, if a photon 706.5 nanometers is emitted, we know that that's the 1s, 3s state, an electron in that state transitioning to the 1s, 2p state. And that was done looking at the Gaussian diagram that you can generate in the NIST database. So our next two elements that we had to identify were mercury and krypton. So these two, we'll see in a moment, they actually cause a little bit of confusion at first, distinguishing between them. So for mercury, we see strong lines across the whole part of the spectrum that we have access to here. And we know there are the two strongest lines that we see in the photograph here are green and yellow. And ultimately, the data matched best with lamp 5. As you can see though, krypton has, at least when you first look at it, has a somewhat similar spectrum, but they are different. And you see with krypton, you see a lot of distinct lines in the far violet part of the range, part of the electromagnetic spectrum, getting into the near ultraviolet. And you see some lines as well in the near infrared. And that's a little bit more apparent here with the digital data. So we matched that with what we see in the database, and we determined this was lamp 8, was krypton. So next, we looked at two molecular gases. Now, these are harder to predict. There is not good reference data available on the spectra of molecular gases. But we see with water vapor here, we determined to be lamp 7. Now what's interesting here is you have the characteristic spectral lines of hydrogen, right? You see about 486, about 656. But as well, you see the peak, the strongest peak for oxygen, 777 nanometers. And so, you know, it stands to reason that this is water vapor here is this spectrum that we're looking at. But something else to note here with molecular spectra, what you end up seeing is what looks almost like a continuous emission spectrum. Now, this is much more apparent here with our next molecule, carbon dioxide. You see a very strong lines all across the spectrum, and again, it looks almost continuous. Of course, we know that it isn't quite. And by process of elimination, we reason that this other molecule must be carbon dioxide, and this is lamp 6, is what we match that to. Now, we also have two mystery elements that were unknown to us. We were given a hint that these elements are commonly used in discharge tubes. Now, that's a good indication that probably what we're going to find here are two noble gases, and that is what we find. So first, we have neon. This is lamp 3. Lots of lines in the 600 to 700 range, which is an orange-red. And we all are familiar with this. It's common in lighting fixtures because with neon, you have a tight grouping of very, very strong spectral lines. It's very, very much characteristic of neon. So finally, we have argon. Now, this one was somewhat difficult to identify because many of the noble gases have similar spectra. Not surprising. And here you have strong lines all across the spectrum, especially as you get up into the infrared, the near infrared, and just the plain red part of the spectrum. You see some very strong lines. And ultimately, looking at the database, we determined that LAMP9 was argon, right? And so that does it for the elements. So thinking about potential improvements, well, it's generally good to have more data to work with. I think that if it were possible to have to have access to more of the near ultraviolet spectrum, more of the near infrared part of the spectrum, that could be useful. Because what we found actually was sometimes the spectra didn't perfectly match NIST. You would have a line, maybe a very strong one, in the database that didn't show up in the experimental data. And that's not too surprising because what you find is it's possible to have it's possible to see slightly different spectra depending on your setup. So just to help with that a little bit, I think it might be useful to have to extend the spectrum that we have access to in this lab. So in summary, here is the lamps paired with their elements. I'm satisfied with the results. This lab was challenging, but I would say rewarding. I learned a lot. And that is about all I have today. Thank you very much for listening.